Good morning, everyone, and thank you for being here today. I am pleased to welcome you to this presentation on forced degradation study. My name is Dr. S.K. Singh, and I hold a PhD in this field. Today, we'll explore the key aspects of forced degradation, its significance, and how it helps us ensure the stability and safety of pharmaceutical products. Over the next few slides, we'll cover the methodology, important parameters, and practical applications. So, let's get started and dive into this important topic together. Let's talk about forced degradation, also known as stress testing. This is a deliberate process where we break down a drug substance or drug product under extreme conditions. The goal here is to speed up the chemical or physical degradation processes that might happen over time. It's important to note that this isn't part of routine shelf life testing. Instead, it helps us understand how the drug degrades and what pathways it might follow. This understanding is crucial for developing stability indicating methods, or SIMs, which are essential for accurate analysis. Now, you might wonder why regulators are so interested in this. Well, they want to make sure that the analytical methods we use can clearly distinguish the active pharmaceutical ingredient, or API, from any degradation products. This ensures we are truly measuring the stability of the drug. Additionally, stress testing reveals what kinds of degradation products might form when the drug is subjected to harsh conditions. This knowledge helps us predict potential stability issues and improve formulation strategies. Overall, forced degradation is a vital tool in ensuring drug safety and efficacy throughout its shelf life. Let's take a closer look at some key guidelines that are essential in our stability testing and validation processes. First, ICHQ 1A R2 emphasizes stress testing, which is crucial for defining how a product degrades over time. This not only helps us understand the degradation pathways, but also plays a vital role in designing effective stability programs. Moving on, ICHQ 1B covers photostability testing requirements, ensuring that our products are evaluated for their stability when exposed to light, which is especially important for products sensitive to light-induced changes. Next, ICHQ2, R1, focuses on the validation of analytical methods. A key aspect here is establishing specificity, often through forced degradation studies, so we can be confident our methods accurately distinguish the active ingredients from any degradation products. Lastly, ICHQ3A and Q3B address impurities, including degradants. These guidelines help us determine acceptable levels and presentation, ensuring the safety and efficacy of our products. Overall, these guidelines form the backbone of our approach to ensuring product quality throughout its shelf life, aligning with the broader theme of maintaining rigorous standards in pharmaceutical development and manufacturing. Let's start by looking at the objectives for our degradation studies. First, we aim to identify the intrinsic degradation pathways. This means understanding how our active pharmaceutical ingredient, or API, breaks down naturally over time under various conditions. Recognizing these pathways helps us predict stability issues early on. Next, we want to establish the degradation products themselves. Knowing what compounds are formed allows us to evaluate their potential impact on safety and efficacy. It's a critical step in ensuring the overall quality of the product. Another key point is supporting the development of stability indicating methods, particularly using HPLC or LC-MS techniques. These methods are essential because they help us reliably detect and quantify our API and its degradants, even in complex mixtures. The method must be able to resolve the API from its degradants, so we need good peak purity and separation. Finally, these insights inform our formulation decisions and help us determine the appropriate shelf life for the product. By understanding degradation pathways and products, we can optimize formulations and storage conditions to maximize stability. Remember, the core of this approach is that our analytical method must effectively resolve the API from any degradants. This ensures accurate detection, which is vital for quality control and regulatory compliance. So, everything ties back to the importance of robust, selective analytical techniques in our stability studies. Now let's take a closer look at typical exposure durations, which can really vary depending on the molecule we're dealing with and how quickly it degrades. Essentially, some molecules are quite stable and can last quite a while under certain conditions, while others break down much faster. This variability is important because it helps us understand how long a material or compound can be expected to perform effectively before it starts to deteriorate. Moving on, we'll also consider typical stress conditions. These are the environmental factors like temperature, humidity, or exposure to light that influence how quickly degradation occurs. Understanding these stress conditions is crucial because they directly impact the exposure duration and ultimately the stability and lifespan of the molecules we're studying. So, by examining both the inherent stability of molecules and the stress conditions they face, we get a clearer picture of their expected performance over time and under different scenarios. Let's walk through the key steps in designing a stability study. First, you'll select the appropriate API or product batch to test. Then, prepare your test solutions or samples carefully to ensure consistency. Next, apply the individual stress types, such as heat, light, or humidity, to simulate various storage conditions. After that, collect samples at specific, designated times to monitor how the product behaves over time. Once you have your samples, analyze them using stability indicating methods like HPLC or LC-MS. These techniques help us identify not only the remaining API, but also any degradants that may have formed. It's important to evaluate both degradant formation and API loss to understand the stability profile comprehensively. Including an unstressed sample as a control is essential because it serves as a reference point, helping us distinguish between natural variability and actual degradation. Our goal is to observe between 5 and 20% API degradation without causing complete breakdown, which helps us determine the stability limits of the product. Overall, this general study design ensures we gather meaningful data on how the product withstands various stress conditions, guiding us in establishing proper storage and shelf life. Now, let's look at an example of a stress condition used in stability testing. Here, the stress agent is sodium hydroxide, or NaOH. We typically use a concentration of about 0.1 normal, which is sufficient to induce hydrolysis without completely degrading the sample. The temperature applied is around 60 degrees Celsius, which accelerates the hydrolysis process. The exposure time ranges from 2 to 6 hours, depending on the specific stability requirements. This particular example involves samples such as active pharmaceutical ingredients or finished dosage forms. To analyze the results, we use a stability indicating HPLC method, specifically with UV detection. This technique helps us identify any degradation products formed during the hydrolysis. The goal here is to understand how the compound behaves under alkaline conditions, which is crucial for assessing its stability and ensuring its quality throughout shelf life. This example highlights how controlled stress conditions can provide valuable insights into the robustness of pharmaceutical products. Let's continue exploring acid hydrolysis, focusing on some key aspects. When we talk about acid hydrolysis, one important point is that it typically involves breaking down complex molecules like carbohydrates or proteins into simpler units. This process is often catalyzed by acids, which help cleave the chemical bonds. It's also crucial to understand that the conditions under which hydrolysis occurs, such as temperature, pH, and acid concentration, can significantly influence the efficiency and specificity of the breakdown. For example, harsher conditions might lead to more complete hydrolysis, but could also cause degradation of sensitive molecules. Connecting this to our overall theme, acid hydrolysis is a fundamental technique in biochemistry and analytical chemistry because it allows us to analyze complex biological materials by simplifying them into their basic components. This process is vital for understanding the structure and function of various biomolecules. So, in essence, acid hydrolysis is both a powerful and versatile tool, one that, when controlled properly, provides critical insights into the molecular makeup of biological samples. Let's take a closer look at this example involving a drug substance, or API. We used a stability indicating HPLC method for analysis, which is crucial for ensuring the drug's stability over time. The detection was carried out with a UV detector, allowing us to monitor the compound effectively. The response factor here is based on the peak area, meaning the area under the chromatographic peak correlates directly to the amount of API present. Now, focusing on the study conditions, we applied stress testing through base hydrolysis. Specifically, we used 0.1 NaOH as the reagent, and the sample was heated to 60 degrees Celsius for 6 hours. This kind of stress test helps us understand how the drug behaves under alkaline conditions, which is essential for assessing its stability profile. Overall, this slide highlights the importance of selecting the right analytical method and stress conditions to evaluate the drug's stability comprehensively. Let's continue exploring base hydrolysis and delve into some additional points. When we talk about this process, it's important to understand that it involves breaking down compounds using a basic solution, typically hydroxide ions. This method is quite significant in various chemical reactions, especially in breaking down complex molecules into simpler ones. One key aspect to highlight is the mechanism behind base hydrolysis. It usually proceeds through nucleophilic attack, where the hydroxide ion attacks the electrophilic carbon atom in the molecule. This step is crucial because it determines the rate and outcome of the hydrolysis process. Another important point is the conditions under which base hydrolysis occurs. It generally requires an alkaline environment, and the temperature can also influence the reaction rate. Higher temperatures tend to accelerate the hydrolysis, making the process more efficient. Connecting this to our overall theme, understanding base hydrolysis helps us grasp how different conditions and environments can influence chemical reactions, especially in fields like biochemistry and industrial chemistry. Recognizing these mechanisms allows us to better control and optimize processes involving hydrolysis. In this slide, we're looking at the specific conditions used in our oxidative degradation study. The stress type we applied was oxidative degradation, which is a common way to test how stable a drug substance is when exposed to oxidative conditions. We used hydrogen peroxide, specifically at a concentration of 3% weight volume, as our oxidizing agent. This concentration is typical for forced degradation studies because it effectively induces oxidation without being overly harsh. The temperature was maintained at room temperature, which helps us simulate typical storage conditions and understand how the drug might behave during normal handling. The exposure time was 4 hours, giving enough time to observe any significant oxidative changes without degrading the sample completely. The sample we tested was the drug substance itself, also known as the API, because understanding its stability in this form is crucial for quality control. For analysis, we used a stability indicating HPLC method, which is specifically designed to detect even small changes in the drug's chemical structure. The detection was done with a UV detector, focusing on the peak area response, which allows us to quantify how much of the drug remains after exposure. Overall, this slide highlights the key parameters we controlled in the oxidation study, emphasizing how we systematically challenge the drug to ensure its stability and robustness in real-world conditions. Now, let's continue exploring oxidation and its complexities. As we delve deeper, it's important to understand that oxidation isn't just a simple process. It involves various reactions and mechanisms that can significantly impact materials and systems. The key points to remember are how oxidation progresses over time, how it can be accelerated by environmental factors like temperature and humidity, and the ways we can control or mitigate its effects. Recognizing these details helps us better predict material behavior and develop more durable solutions. This connects directly to our overall theme of understanding corrosion processes and improving material longevity. So, keeping these aspects in mind will enhance our ability to address oxidation-related challenges effectively. Let's walk through the study procedure. First, we weigh the solid active pharmaceutical ingredient, or API, and expose it to 80 degrees Celsius in a hot air oven. After 24 hours, we remove the sample and allow it to cool down to room temperature. Next, we prepare a test solution at the targeted concentration to simulate real-world conditions. We then analyze this solution against an unstressed control using a validated HPLC method, which helps us measure any degradation. Now, focusing on the study conditions, this is a thermal or heat degradation test, specifically using dry heat at 80 degrees Celsius for 24 hours. The samples can be drug substances or solid dosage forms, placed either in open Petri dishes or stability vials to ensure proper exposure. The analytical method we use is a stability indicating HPLC, which is essential because it can accurately detect and quantify degradation products. Detection is achieved via a UV detector, focusing on peak area response to assess the extent of degradation. This thermal degradation process helps us understand how heat impacts the stability of our API, which is crucial for ensuring the safety and efficacy of the final product under various storage and handling conditions. Now, moving on to the experimental data related to heat or thermal degradation, I want to emphasize that this is a continuation of what we've been discussing earlier. As we look at the data, you'll notice how the materials respond to increasing temperatures, which is crucial for understanding their stability and potential applications. Thermal degradation typically involves breaking down of the material's molecular structure when exposed to heat, and observing this process helps us determine at what point the material starts to lose its properties. This data gives us insights into the temperature thresholds and degradation patterns, which are essential for predicting the material's performance in real-world conditions. By analyzing these results, we can better tailor materials to withstand specific thermal environments, ensuring safety and durability. Connecting this to our overall theme, understanding the thermal degradation behavior helps us optimize processing methods and improve material formulations. It's a key step in developing materials that are not only effective, but also reliable under various thermal stresses. Let's walk through the study procedure. First, we prepare both control and test samples. The test samples are then exposed to a defined amount of UV and visible light, simulating conditions that could cause photodegradation. Meanwhile, the control samples are protected from light, typically wrapped in foil, to serve as a baseline for comparison. After the exposure, we prepare solutions from both the stressed and control samples for analysis. Next, we analyze these samples using high-performance liquid chromatography, or HPLC, which is a stability indicating method. This allows us to precisely measure any degradation products formed during the exposure. The detection is done using a UV detector, focusing on the peak area response to quantify the drug content and degradation. Regarding the study conditions, the stress is specifically photodegradation, meaning we're simulating light-induced degradation. The light source combines UV and visible light, with UV exposure reaching at least 200 watt-hours per square meter, and visible light exposure reaching a minimum of 1.2 million lux-hours. We test both drug substances and drug products, and samples are placed in open or closed containers as appropriate. All of this follows the guidelines outlined in ICH Q1B, specifically Option 2, which standardizes the conditions for photostability testing. By carefully controlling these parameters, we can evaluate how the drug behaves under light exposure, ensuring its stability and safety throughout its shelf life. Now, moving on to the experimental data, specifically the photodegradation results that we continue to explore. As you can see here, we've gathered more detailed insights into how our materials degrade under exposure to light. This data is crucial because it helps us understand the stability and longevity of the materials in real-world conditions. What's particularly interesting is how the degradation rates vary depending on the environmental factors and material composition. These insights allow us to optimize our formulations for better durability. Remember, The overall goal is to improve the performance and lifespan of these materials in practical applications, and this data is a key piece of that puzzle. So, by analyzing these photodegradation patterns, we can identify the most resilient formulations and work towards more sustainable, long-lasting solutions. This ongoing research brings us closer to achieving that goal. For further support, please feel free to reach out to us. We're here to help you with any questions or additional information you might need. Don't hesitate to contact us through the provided channels. And with that, I want to sincerely thank you all for your time and attention today. Your engagement is truly appreciated, and I hope you found this presentation valuable. Thank you again, and I look forward to connecting with you soon.